Hello students, welcome to my YouTube channel Candid Chemistry.
Let us discuss the nomenclature of alkanes in detail. In case of common or trivial names, in the early days the compounds were named on the basis of their history, the method of preparation or the name of person who was working on it. For example, the name marsh gas was given to methane because it was found in marshy places. Acetic acid derives its name from vinegar. In Latin, acetum means vinegar. For alkanes with 5 or more carbon atoms, the root word is derived from Greek or Latin numerals indicating the number of carbon atoms in a molecule, and the name is completed by adding A and E as a suffix. For example, pentane, hexane, heptane, etc. The common or trivial names are applicable to all isomers of a given molecular formula. The prefix N, iso, neo are however to differentiate between isomers. Let's say if the carbon is attached to 1 or 2 carbon atoms, then it is supposed to be called as N-butane. If the carbon atom is attached to further 3 carbon atoms, it is called isobutane. And if the carbon is attached to 4 different carbon atoms, it is known as neopentane. In case of IUPAC or IUPAC names of alkanes, we have to follow certain rules. For example, first rule is locate the largest continuous chain of carbon atoms independent of direction of the chain. It is called main chain, stem, principal, or even parent chain. The example has been shown below. The second rule is if there are 2 or more chains of equal lengths, chain with longer number of branches is selected as the main chain. It has been illustrated in the example again. Third rule is number the main chain starting from the end nearest to the substituent. Now substituent is anything which is not the part of main chain. Number 4, when the 2 identical substituents are present at equal distance from either side, number the chain starting with the end which gives their minimum sum. Since the sum of number 2, 3, 5 is 10, which is less than 2, 4, 5 is 11, the correct numbering starts from the right hand side in case of the example shown in the diagram. Next rule is the position of substituent is indicated by number of carbon atom to which it is attached. Then next rule is the number is prefixed to the name of group separated by hyphen. Names of alkyl groups are written before the name of parent hydrocarbon in alphabetical order or in order of increasing size separated by hyphens, as shown in the diagram 3-ethyl 2,3,5-trimethyl-hexane, where the positions are shown and the different types of same substituents have been named along with the prefixes di, tri, hexa, etc. When 2 or more like groups are present, their numbers are indicated by prefixes di, tri, tetra, etc. The numbers are grouped together and are separated by commas as shown in the diagram. If 2 identical groups appear at the same carbon atom, the number is separated twice. The longest chain of the substituent is numbered starting with the carbon attached directly to the main chain. Parentheses are used to separate the numbering of substituent and main chain. These structural formula and names for simple alkanes are shown in the following table. Methane, ethane, propane are shown in the form of formula and also in the form of line structures. Let us talk about the physical properties of alkanes. Alkanes containing up to 4 carbon atoms are colorless, odorless gases, while pentane to heptane or decane are colorless, odorless liquids. The higher members from C18 onwards are waxy solids which are colorless and odorless. Alkanes are non-polar or weakly polar and are insoluble in polar solvents like water, but soluble in non-polar solvents like benzene, ether, etc. The physical constants like melting points, boiling points, density, etc. increases with increase in number of carbon atoms, whereas solubility decreases with increase in molecular mass. The boiling point increases by 20 to 30 degrees Celsius for addition of each CH2 group to the molecule. Melting points of alkanes also increase with increase in molecular mass. Talking about reactivity of alkanes or paraffins under ordinary conditions are inert towards acids, alkalis, oxidizing and reducing agents. As the word paraffin itself means, param is little and affin's affinity. However, under suitable conditions, alkanes do undergo two types of reactions, either substitution reaction or thermal and catalytic reactions. These reactions take place at high temperature or on absorption of light energy through the formation of highly reactive free radicals. Non-polarity of the bonds. The electronegativity values of carbon 2.5 and hydrogen 2.1 do not differ appreciably, and the bonding electrons between carbon-hydrogen and carbon-carbon are equally shared, making them almost non-polar. Inertness of sigma bond. In a sigma bond, the electrons are very tightly held between the nuclei, which makes it a very stable bond. A lot of energy is required to break it. Moreover, the electrons present in a sigma bond can neither attack on any electrophile nor a nucleophile can attack on them. Both these facts make alkanes less reactive. Structure. Alkanes are the simplest organic compounds comprised connected by a single bond. They have a general formula of CnH2n plus 2, a relationship that also defines the maximum number of hydrogen atoms that can be present for a given number of carbon atoms. C4 alkanes are shown below in a variety of representation. As the number of carbon increases, then other isomeric structures are also possible. Let's talk about the most important reaction of alkanes, that is radical substitution reaction. The substitution of RH by X provides the alkyl halide RX and HX. Alkanes which are RH relatively reacts in the order tertiary to secondary to primary and then methyl group. Halogens which are X reacts in the order of fluorine to bromine and last but not the least iodine. Only chlorination and bromination are useful in laboratory. Reactions proceed via radical chain mechanism. Alkanes react with chlorine and bromine in the presence of sunlight or UV light or at high temperature, resulting in successive replacement of hydrogen atoms with halogens called halogenation. Extent of halogenation depends upon amount of halogen used. Reaction of alkane with fluorine is highly violent and results in a mixture of carbon, fluorinated alkane and hydrofluoric acid. Iodine does not substitute directly because the reaction is too slow and reversible. The order of reactivity of halogens is fluorine to bromine and then iodine. Halogenation is believed to proceed through free radical mechanism. It involves the following three steps. Cycloalkanes. Another type of molecule containing only sp3 hybridized carbon and hydrogen atoms connected by single bonds is possible with a ring of 3 or more carbon atoms are cycloalkanes. How to name them? According to IUPAC system, cycloalkanes with one ring are named by prefixes cyclo to the name of corresponding alkane having same number of carbon atoms as the ring. They may be called cyclobutane, pentane, alkane, etc. The substituents are numbered in such a way that the sum of numbers is kept minimum. If the alicyclic hydrocarbon is unsaturated, the rules applied to alkenes for double bond or alkynes for triple bond are used. Multiple bonds are given the lowest possible number. For example, 3-methyl-cyclopentene is the name, not 5-methyl-cyclopentene. In the similar way, another compound to be named is 4-ethyl-1-methyl-cyclohexene. Talking about the physical properties of cycloalkanes, like alkanes, the low polarity of all the bonds in cycloalkanes means that only intermolecular forces between molecules of cycloalkane are the very weak dipole-induced polar forces, also known as London dispersion forces, which are easily overcoming. Like alkanes, cycloalkanes also have low melting and boiling points. They have a general formula of CnH2n, no two less hydrogen atom compared to analogous alkanes. The C3 to C6 cycloalkanes show different representation, and in terms of reactivity, They have the similar reactivity with those of closely related alkanes which have same types of bonds. Since carbon and hydrogen have very similar electronegativities, both the carbon-hydrogen and carbon-carbon bonds are non-polar. As a result, cycloalkanes, like alkanes, are not very reactive functional groups.
Students, I hope this video lecture was helpful to you. If you like this video, give it a thumbs up and don't forget to subscribe to my YouTube channel Candid Chemistry. Thank you.